kiddos, in this video we're going to talk a little bit more about bonding. Specifically, we're going to go into just a little bit deeper level about what is a bond and like why does a bond form. I mean, since you were in elementary school, middle school, freshman classes in high school, sometimes you talk about bonds. You said I've got ionic bonds and I've got covalent bonds, and in covalent bonds things are shared. In ionic bonds, the things are shared. Electrons are shared. In ionic bonds, then electrons are transferred from one to another, and I get a cation and an anion, and then I get electromagnetic attraction, all of that jazz. So I want to go into a little bit more detail and show maybe a little graph that will explain a little bit more about what the bond is and how that relates to the length of a bond and the energy in a bond. So we're going to take a simple case. We're going to take a hydrogen-hydrogen bond, okay? So we've got two hydrogens. These are our two hydrogen nuclei. And obviously then each of those nuclei has one electron, okay? These are hydrogens. And remember that, those electrons are going around in an electron cloud, right? In the orbitals. It's not like they're going around these nice, neat circular paths, okay? And so what's going on here to form a bond is there are essentially three interactions that are going on, okay? And so I want to make sure that you're aware of the interactions. Then we'll look at a little graph that'll talk a little bit about the energy. So what are the interactions that are going on? Well, there's an interaction here that is between the two nuclei, okay? And the interaction between the two nuclei is that nuclei have what kind of charge? Well, obviously, nuclei are positively charged. And what do like charges do with each other? Okay, they repel each other. So the first interaction then is that there is repulsion. Anytime the two atoms are trying to come together, one of the interactions is that there's a repulsion between the two nuclei. Okay, so that's the first one. The second one is that there's going to be another repulsion. Okay, and that is between, so repulsion. Now remember, force of repulsion. So there's a repulsion between electrons. Or we could say between electron clouds, maybe. In our case, we're only dealing with one electron each, so it's between the clouds, or between the individual electrons. So the electrons are also repelling each other. Why? Well, because electron, those are those are both the same charge, right? So like charges are going to repel each other. That's also going to be a repulsion. So you might be thinking immediately in your brain, well, like, that is, okay, great. So you've told us, those things, and those all would speak to there being a repulsion, that no bond forming. So what's the other interaction? Well, the third interaction, okay, is sort of it happens twice, essentially. So here's what happens. So I've got a nucleus. This nucleus over here, okay, is attracted to, and let me actually grab a different color here. This nucleus is attracted to this electron. You'll notice that I drew the arrows a little bit differently. That means that those are pulling towards each other. They're going to each other. This nucleus has a positive charge. It is attracted to this electron cloud over here and pulling on it. While that's happening, okay, there is also a force of attraction between the other nucleus and the other electron cloud. Okay? So what's the third interaction then? Well, the third interaction is while I'm leaning over the writing. So the force of attraction between one nuclei and the opposite electron cloud. And it's not really one nuclei. Well, it is, but that happens twice, right? Okay, so that's a times two interaction. So there are three interactions here that you're looking for. Okay, the nuclei want to repel each other. The electron clouds want to repel each other. But this nucleus is attracted to this electron cloud. This nucleus experiences a force of attraction between this electron cloud. That's going to lead to the bond. So let me pause there. I'm going to erase that, and then I'm going to show you a little graphical analysis that's going to explain all that, and we'll have to do directly with bond length and bond energy. Okay, so let's talk a little bit about what this graph means real quick. Okay, so the potential energy, that's my y-axis. Internuclear distance is my x-axis. You might be wondering why I put my x-axis up here when I would normally put it down here. Well, that's because we're going to be going down into the negative part. Okay? That's what's important to us. Now, you should already sort of know from previous science classes, but if maybe not, that low energy states are more stable. That's what systems are trying to get to, is to a low energy state. And so the lower the potential energy of that system, the more favorable that state. And that's exactly why a bond is going to work this way. So internuclear distance over here, that's the distance between the nuclei. So remember when I drew those two models, so there's essentially what that means is there's going to be an optimal distance where the attraction between this nucleus and this nucleus overcomes the repulsion between the two nuclei, overcomes the repulsion between the electron clouds. Okay? So there's sort of a spot that's exactly where you want it to be. Okay? So let me draw what this actually sort of looks like for the bond formation. We're going to get a state like this. We're going to go down, and then we're going to sort of taper off to that. That graph isn't exactly what it looked like. I probably should have made that a little bit narrower, but close enough for what we're doing. Because what I need you to understand is the relationship between the energy and the distance and all of that. So what this means is that this is, again, a really small internuclear distance where they're really, really close together. And if they're really, really close together, then that force of repulsion between the two nuclei are going to really, you've really got to force that to happen. You know that you have to force that to happen because that's how nuclear fusion would happen, right? If you really jam those two nuclei close enough together that they could actually fuse, remember we're talking about two hydrogens, then that would form a helium, a lot of energy would be released, that would be fusion. So that requires a lot of potential energy to make that happen. So up here is the case where they're really, really, really too close together, okay? We're going to go down. You'll see that we go down, and we're down here to a point at the bottom of the well, where essentially at this point right here, the distance is perfect, and it's at really low energy. Okay, in other words, the forces of attraction between this nuclei and this electron cloud and this nuclei and this electron cloud are optimal. This is the most stable state. Okay, minimizing the repulsions between the two nuclei and the electron clouds. Those forces of repulsion are being overcome by the force of attraction between them. Okay, and then as they would start to separate out a little bit more, you might get situations where they'd actually be, not bonded together at all, where I'd have two hydrogens just out there floating together. They're not bonded together in any way, shape, or form. And then you might, in the intermediate, obviously have some stages where they were a little bit further apart, not really at what we would think of as the optimal distance between them. Now, here's why this is important, because at this point, okay, which is the lowest energy state, this is negative 436 kilojoules per mole. You don't need to memorize that number or anything, but what is important is that it is the lowest energy. Okay, lowest energy means that's the point where that bond is going to happen. Now, up here, if we also drew ourselves a little line up to the x-axis, then let me make sure that I get my number correct. I would get a distance of 0.74 angstroms. Now, why do those two things matter? Well, because that gives us two things that we really sort of need to know. That gives me the bond length, and it gives me the bond energy. Writing is hard. Okay? Those two things are really incredibly important for us. We need to know those two things. We can do a vast number of calculations off of those things. But more importantly, what is a bond? So the bond, okay, is the state at which you have forces of attraction at the lowest possible energy state, which means it's at its most stable state. That's why those bonds are going to form. Stability. Okay? Again, I know a lot of times, and I've probably been guilty of this in the past, you might hear some professors saying, oh, it wants to be at that state, or that's, sharing is caring, and no, none of that, that's all garbage, right? It's the lowest energy state, that's the most stable state, that's where it needs to be. Okay? Not even needs to be, it's where it's most stable. Watch your words. I have to also. Okay? Thanks, kiddos.